Alright, so now we're looking at this interesting problem, and sometimes we have problems that we work through that I sort of don't like for whatever reason. Maybe um, it's not very useful or straightforward, or maybe it uses things that I think are a little beyond what should be expected at this point in the course. But the reason I don't like this problem is because it's wrong. Part A is correct, but Part B is wrong. And so we can't really talk about Part C at all because Part B is wrong. So anyways, let's talk through Part A and then we'll start talking about Part B. So we have an angle between two vectors, which is essentially just the way that you would think about it geometrically. So if you've got two vectors here, then the angle between them would be defined like this. And there's a formula for it in terms of just facts about these vectors x and y. You take our cosine of inner product over the norms. And this arc cosine of whatever will give you an angle, and that angle will be precisely this theta. Now, we need to check that this makes sense. So note that for if we have x and y which are non-zero vectors, then the norm of x and the norm of y will both be non-zero, because the only way for the norm of a vector to be zero is if the vector is zero. And so if we look at arc cosine or cosine inverse, we'll actually know before moving to that. So if we just look at x, inner product of x and y over the norm of x times the norm of y, well, we know that this is just an absolute value, because this is just this inner product is a number, and on the bottom we've got numbers. So this is norm of x, y over norm of x times norm of y. And we know by theorem 1-1-2 that the norm of the inner product is less than or equal to the dot product. And then we keep the denominator the same, but this is just 1. So our cosine of xy over x times y is defined. And it's defined because our cosine of a number means, okay, cosine, let's see, our cosine of x will give you the angle such that cosine of theta equals x. So arc cosine, there's only so many values that you can take the arc cosine of. In particular, if you think of the range of cosine, cosine can go between positive 1 and negative 1. So if you take the cosine of any angle, it will be between negative 1 and positive 1. So if you take the arc cosine of a number, you have to take the arc cosine of a number which is between negative 1 and 1. Because if it's not between negative 1 and 1, then you can't take the cosine of anything to get that number. So arc cosine of 2 is not defined, because you can't take the cosine of any real number and get the number 2. It's not possible. But we see here that given any non-zero vectors x and y, if we look at the absolute value of this inner product over the two norms, it will be less than or equal to 1, which means that if you remove the absolute value, it's between negative 1 and positive 1, which is exactly where we need it to be in order to be able to define our cosine. Okay, so with that being out of the way, by the way, in the problem statement it says which makes sense by theorem 1-1-2, so we did actually have to do a little bit of work to prove that that is actually the case. But yeah, it just follows by theorem 1-1-2, which we used in that inequality. Okay, so t is angle preserving if this thing holds. Prove that if t is norm preserving, then t is angle preserving. So suppose that the norm of tx is the norm of x for every vector x. Okay. T is assumed to be linear. That's because I guess the linear transformation t is angle preserving if t is 1 to 1 and blah blah blah. So prove that if t is norm preserving, it's implied in that statement that t is also linear. And in fact, we need linearity to do this proof. So if we look at two vectors x and y, and we suppose that tx equals ty, then we just subtract the ty to the other side and we get this. And then by linearity, this is just t of x minus y equals 0. And so if this vector is 0, then its norm is 0. By the way, this is the 0 vector here. And so the norm of the 0 vector is 0. So if the norm of this vector is 0, well, the t is norm preserving, so we can remove the t there. So the norm of x minus y is 0. But the only way for the norm of a vector to be 0 is if the vector itself is 0. So x minus y is the 0 vector, which means that x equals y. So t is 1 to 1. Because that's how we check that t is 1 to 1. We prove that if you take x and y, if their images under t are equal, then x and y themselves are equal. Okay, so what do we need? We need angle preserving t is 1 to 1, and for x, y, and I equal to 0, we need the angle of tx, ty to be angle x, y. Okay, so now what we have is exercise 1.7a says that norm preserving linear maps are inner product preserving. Inner product preserving. So for x and y not equal to 0, the angle of tx and ty is, let's see here, arc cosine. I'll just write cosine inverse because that takes less time. So let's see here. I'm going to write it like this: tx comma ty over tx times ty. This is sort of weird looking notation, but it allows me to write the numerator and denominator a little bigger without having to add a whole bunch of unnecessary parentheses, which you have to do if you add them into the entire same line. Okay, so now cosine inverse. Now for the numerator, for a map to be inner product preserving, it means the inner product of tx and ty is the inner product of x and y. So we can replace that with x and y. And then also, this is norm preserving. So tx and ty on the norms of tx and ty become the norms of x and y. And by the way, this actually confirms that, I guess before, so we divided by the norm of tx times the norm of ty in the previous step. I guess you can't technically do that until you confirm that those things are non-zero. But they're non-zero because x and y are non-zero vectors, and so their norms are non-zero. So I guess if you wanted to be super rigorous, you would have to write this in the reverse order. You start with the angle between x and y, and you prove that it's equal to this cosine inverse of x, y over norm of x times norm of y. And then you convert inner product of x and y to inner product of tx and ty, and you change the denominator to norm of tx times norm of ty, which you know is well defined because norm of x times norm of y is non-zero. Okay, so hence t is angle preserving. Okay, and now we move on to b. So b is the part that is wrong. So basically what from just using language of like more advanced linear algebra, what's happening is it's saying that if this transformation, if the eigenvectors of this transformation form a basis of Rn, and all the eigenvalues have the same magnitude, then that's equivalent to t being angle preserving. But I looked this up online, and that's how I was able to figure out that this was false. I think what happens is, like, so I mentioned eigenvalues there. That's what these lambda i's are. They're eigenvalues. It turns out, I think there is a statement which is equivalent to t being angle preserving, but instead of referring to the norms of the eigenvalues, I think it involves the norms. No, I think it involves the singular values. So, of course, this is beyond the scope of this is beyond the scope of the background that's expected for this textbook, and so it probably wouldn't be included as an exercise. And so I'm not even going to discuss a condition which is equivalent to t being angle preserving, although I'm pretty sure there exists one. However, for this, all we need to do is we need to prove that this is wrong. So we just need to come up with an example. And there's an example I found on Stack Exchange, and I'll show that. So let's see, we need a basis, we need some xn's and some lambda n's and some t. So let t be the linear transformation from R2 to R2. It's going to be 1, 0, minus 2, minus 1. And then, let's see here, so x1 is just going to be 1, 0. x2 will be 1, 1. Lambda 1 is 1. And lambda 2 is minus 1. So we need tx1 to be lambda 1x1, and we need tx2 to be lambda 2x2. So let's check that. So tx1, well, this is just 1, 0, minus 2, minus 1, times 1, 0. Well, that's just going to be 1, 0, which is just 1 times x. It's 1 times the vector 1, 0, which is lambda 1 times x1. And so now if we look at tx2, this is 1, 0, minus 2, minus 1, 1, 1. So this is 1 minus 2 is minus 1, and 1 times minus 1 is minus 1. So this is minus 1 times 1, 1, which is lambda 2 times x2. Okay. Also, x1 is orthogonal to x2. So x1 and x2 form a basis of R2. And that should be pretty straightforward, because if you take x2 minus x1, you get 0, 1, and so you get the standard basis for R2. Alright. Now, we'll define x is 1, 0, and y is 0, 1. So what are we going to do? Prove that t is angle preserving if and only if all of the lambda i's are equal. So what we have here, also, the norms of all the lambda i's need to be equal, and that's obviously true because the norm of 1 is equal to the norm of -1. They're both 1. So now what we need is we need two vectors, x and y, such that their angle is not the same, the angle between x and y is not the same as the angle between tx and ty. So if we look at the angle between x and y, well, just visually you can see that's a 90-degree angle, so it should be pi over 2. But if we want to do this using the formulas that we have, then the angle between x and y is going to be cosine inverse of xy over norm of x times norm of y. And so norm of x and norm of y are both going to be 1, so the denominator here is 1. And the numerator, the inner product of x and y, is going to be 0. So this is just cosine inverse of 0, and we think what angle can we take the cosine of to get 0? And just by the unit circle, you know that the cosine of pi over 2 is 0. So our cosine of 0 is pi over 2. But now let's look at the angle between tx and ty. And this is going to be equal to cosine inverse of tx ty over norm of tx times norm of ty. So what is this going to be? If we look at tx, well, x and y are easy to it's easy to compute the vectors. In fact, we've already done tx because x is equal to x1, so it's just going to be 1, 0. So this is the inner product of the vector 1, 0, and here I'll put this on the next line. I want to make this look a little bit nice. Cosine inverse of 1, 0, and ty. So if we take t and multiply by the matrix 0, 1, we're going to get a -2 and a -1. Then we divide by the norms of these vectors. Okay. Now, I'm not quite sure what this is, but if we take the denominator, it's not going to be 0. It's going to be some number. It's going to be, well, the thing on the left is 1, and the thing on the right is going to be, what, square root of 5, I think? Yeah, square root of 2 squared plus 1 squared. So denominator will be square root of 5, and numerator will be 0, -2 times 0, so it's -2. So this is cosine inverse of -2 over square root of 5. I don't know what that is, but I do know that whatever that number is, it's not 0. And so the only way for our cosine to be pi over 2, well, there's only one value that we could, there's only one, well, okay, so cosine of pi over 2 is precisely 0. And in the domain of our cosine, so if you go, let's see here. So for our cosine, we can only plug in numbers between -1 and 1. I guess when we look at arc cosine, you have to choose a range of values that you can use, because cosine of pi over 2 is 0, but also cosine of pi over 2 plus 2 pi is 0. So you can only use one period of the cosine function, but the point is, cosine inverse of whatever this number is, it's not going to be pi over 2. And let's see here. I guess the proper way to prove this would be that arc cosine is injective, or it's 1-to-1. Yeah, between -1 to 1 and its range, which should be 0 to pi. Okay, let me think about this a little bit. So, I mean, yeah, what I'm doing right now, it doesn't really matter. All that really matters is that this number is not equal to pi over 2. So if we're looking at numbers that we can take the arc cosine of, so if we take the arc cosine of 0, we get pi over 2. If we take the arc cosine of -1, 1. So if we take the arc cosine of 1, we want something that cosine inverse of x equals 1. So it's going to be so x will be cosine of 1. No, this doesn't make sense. No, cosine inverse of 1 equals theta. So 1 equals cosine of theta. So we want cosine of theta to be 1. So we could choose cosine is here over here. So if this is 1, this has to be 1 and this has to be 0. And so this is when the angle is 0. Oh yeah, and then it looks like then cosine inverse of -1, we have like this, -1, 1, and 0 sort of. So this is going to be pi. And this is pi over 2. Oh yeah, okay, so yeah. So this is y equals cosine inverse of x. So the thing is, you can prove, well actually, we can just sort of look at this and see that arc cosine is always strictly decreasing, which and it's over a bounded domain, so it's bijective, and so it won't take on the same value twice. So you can't plug in two numbers into arc cosine and get the same value. So we're plugging in a number into arc cosine which is non-zero, and so we're not going to get arc cosine of 0. Okay, so t is not angle preserving because the angle between x and y is not the same as the angle between tx and ty. Okay, so part B is wrong. And then part C, we can't even answer that because we don't really have a grasp on what angle preserving linear transformations look like, because B is not true. So I think you can answer C, but it takes some more advanced techniques that we don't really have at our disposal now. So I guess this exercise sort of shows us that, yeah, I think this is sort of annoying. Like, if you were to get assigned this in a class, that would be extremely annoying because you're being asked to prove something that isn't true. But there is, I don't know, I think it's sort of nice or reassuring to know that professional mathematicians can have typos or small mistakes in textbooks, because math is inherently a very difficult subject, particularly in this course if this is like your first time taking a rigorous math course, or like maybe your second if you've already taken a rigorous linear algebra course. Yeah, math is difficult and proofs are difficult, and it's easy to get something it's easy to forget a small detail somewhere. And even the best mathematicians do it from time to time, and it's not a big deal. So if you make mistakes, it's not a big deal. It happens, and yeah, you just learn from it and move on. So yeah, I just wanted to go over this exercise, do the part that is doable, and then make very clear that part of it is a false statement and show why it is false. And alright, so that's all we can do, and so we are done with this exercise.